Hi guys,
Good morning.
how are you?
Good. How are you?
I'm doing good, thanks. Looks like. So, don't forget we have a quiz today. I actually set the quiz to become available at 11 this morning. So I will only talk for about a half an hour. And then we'll end class. And if you want to start the quiz right after I finish talking, you are free to start it. It's a 24-hour availability window, so it will be available until 11 o'clock tomorrow morning. So if you don't want to start it right now, you want to review, you want to do other things, you can. But just to let you know, you can start it this morning. And I'm just going to end class early because we're going to spend a couple days on this topic. But that'll give you a chance to work on it here in class instead of having to take time away from other things. Okay, so all very exciting. Also, don't forget, you guys, tonight your homework for chapter 3.1 is due, and then your classwork for 3.1 is also due. So don't forget that's due at midnight tonight. I do accept late stuff, but try to get it in so this stuff doesn't overwhelm you. We really don't have a whole lot of time left to this semester. We've got today's class. We have a holiday break, which is nice. And then we come back for a full week next week of classes. And then that's basically the end of our classes. And then the following week, right? So basically 2 weeks from today, we have quizzes, and then we have our projects that's due. Okay, and then I would actually like to have it so that you guys can present your projects to the class. And I'm kind of looking into seeing how that will work with Zoom. Maybe I can share the screen with you. I'm going to try to figure that one out. But we'll talk about that on Monday when we come back from our break. Anyway, let's go ahead and move on. We're in chapter 3.2. So 3.2 is called antiderivatives. So we're going to talk about derivatives. We did derivatives in chapter 3.1, but we're going to talk about derivatives in terms of antiderivatives and how all this helps us with motion. What do we need to think about that with motion? Okay, so this is where we're at. Antiderivatives is really what we're going to be covering specifically. When we think about we have a function and we take its derivative. Taking an antiderivative is bringing ourselves from a derivative back to the original function. Okay, so if we say that a derivative of a function, say f of t, where t is, say, in time, it's a function of time, we would say d f of t dt, right? So I'm taking, which we've sometimes written as d dt of f of t. Okay, and I'm going to assign that equal to some other function here. Hang on a sec. Assign it equal to some other function here. Okay. So in case you're coming late, just to let you know, we have a quiz this morning, and I've said it, we're going to end at 11 o'clock so that you guys can start your quiz at 11 if you want. You don't have to. You have a 24-hour availability window, but you can. Okay, so I have a function f of t. I take its derivative, and I'm going to make that derivative equal to g of t. Okay, that means what I can now do is this. I can say my function f of t is equal to the integral, or the antiderivative, of its derivative, right? So this is the antiderivative, right? This here, it's also called an integral. Doing integration is the process of finding the antiderivative. These are two sides of the same coin, the coin being our function, right? So I have a function, I take its derivative. If I take the integral of that derivative, I get the function back, which is exactly what we're trying to say right here. Okay, so there are all sorts of rules for how I can do antiderivatives. Okay, and there's a whole bunch of theories behind, like, what does it mean and what are we trying to do? Okay, I'm just gonna give you the high level view of all this stuff. But how do I actually take this? What's called an integral to get the antiderivative, right? I need some rules that are going to help me. Okay, so some rules that we're going to talk about that are going to help us with this integration. The first one is what we call the power rule. Just like we have a power rule for taking the derivative, we have a power rule for finding the integral. So say I'm going to take the integral of x to the n dx, right? This is like x squared, x cubed, something like that, right? When I go to do this, I have my variable, I increase n by 1, and I divide the whole thing by my new exponent, okay? Now I have to add in what's called a constant term. Okay, so let's write this down in a different color. So this is a constant term. And this helps us figure out like what's the specific solution, right? And we need other values. We need what's called initial conditions to help us find this constant term, okay? But I need to have that if I'm just raw integrating. Also, this will also work for when n is not equal to a -1. You can imagine x to the -1 plus 1, it's equal to 0, all over -1 plus 1. I'm going to have a divide by 0 problem if I try to do the power rule like that. So I need a new rule to help me do it when I have, when my exponent is -1. So I'm going to integrate from x to the -1 dx. This, by the way, is also going to look like 1 over x dx. Okay, right? If I have it like this, I usually write it like that. I can leave it like this either way, but just so you know, this is x to the -1, right? This says this x belongs on the other side of the dividing line. See, somebody's asking me about the tests, and I am still grading them. They look good so far. It takes forever to grade things online, and so I appreciate your patience. So I'm going to definitely, I will have them graded over Thanksgiving break. It's just, it's for some reason it takes so much longer to grade on the online. I think it's because I have to move the mouse around, and it's, you know, I have to make comments and stuff. And then when I do tests and exams, I actually have to download the test, make comments, save it, and then, you know, store it. So it's a lot more tedious than if I had a paper and I could just write it out. Anyway, so over Thanksgiving break, I will be posting your exams, but they look good so far. All right, so when I have this, right, so when my exponent is equal to -1, my rule is I take the natural log of the absolute value of x. And then don't forget your plus c. Let's try some trig stuff. So if I've got the integral of sine of a times x, where a is some constant term, like it's 3 or pi or whatever, it's just some constant term. Sine of a times x dx. Okay, when I go to take the integral of the sine, right, remember when we take the derivative of the sine, it's positive cosine. But you have to remember that this function here is a derivative of something. And I'm trying to find out what function this is a derivative of. So what function will give me the derivative that's equal to the sine? Well, if I take the derivative of cosine, I'm going to get negative sine. So maybe it's minus the cosine. That'll give me positive sine. Again, I've got my chain rule, that a over there. So what I'm going to do with that chain rule is 1 over a minus 1 over a cosine of ax plus c. Okay, this a here is, it's a chain rule. Okay, there's a chain rule with integration as well. And we'll do cosine of a times x dx. Remember, this is a derivative already. So what function will give me the derivative of cosine? And the answer is my sine. Now don't forget the 1 over a, because that's my chain rule. And I still have the same argument on the inside, plus c. Okay. Let's do this with exponentials. E to the ax dx, e to the x, but x could be multiplied by some constant term a. Okay, so when I go to take that integral, okay, I have my chain rule, this 1 over a times e to the ax plus c. Okay, always remember your plus c's if I don't have any bounds on my integral. Okay, and then let's just talk about, we'll do this one. So c dx, where c is a constant. Let's write this out. So c is a constant. If I were to integrate that, I'm going to get c times x plus, you know, some other constant term. I'll call it c1. different constant. Okay. All right, so let's do some examples where we can take a look at what's happening. Okay, so we've got, oops, we've got a ball is thrown at 0, 0, 2, right? So this is in 3 dimensions. This is an R3. So 0, 0, 2. With initial velocity, v of t equals 1 minus 1, 3. So initial velocity, this is going to give us an initial condition, which is going to help us solve for those c values. Let me just write that down. So initial conditions help us to solve for our constant term c. Right, and we do that plus c at the end of our integral. So our initial conditions help us figure that out. So find its position as a function of time. Assume that the acceleration due to gravity g is equal to 10, which means that in terms of 3 dimensions, right, our gravity, we're thinking about things as, right, here's z, x, and y. So x and y are where we're going left and right, and z is our up and down. So gravity is in our 3rd dimension, minus 10, because it's pulling us down, okay? So now let's just write down what we have. So acceleration is a derivative of velocity, right? So, so that means it's v prime of t, right? So I had to take the derivative of velocity to get acceleration, okay? Which means that my derivative of velocity is equal to 0, 0, minus 10. All right, good. So I'm already starting to deal with this. So now what I can do is I can say to actually get the velocity, I can take the integral, oops, with respect to t, I can take the integral of both sides, 0, 0, minus 10 dt. And that's going to give me my velocity, right? Because this is the derivative of velocity. So if I take the integral, the antiderivative, I'll get my velocity. Now, how do I do this here? This is what's going to happen is I'm going to take the integral of 0 dt, the integral of 0 dt, the integral of minus 10 dt, right? So don't worry that it is a vector. I have an x, y, and a z component. I just take the integral of each individual piece, and then the answer becomes a vector also, okay? So now my v of t is equal to 0. When I take the integral of 0, I get 0, but I have a constant term I have to deal with. So this becomes 0 plus, and I'll call it c1. I take the integral here, this becomes 0 plus, I'll call it c2. And then here, watch, I get a minus 10 times t, right? And then I'll call that plus c3. Okay, so this is for my x, my y, and my z. So I took the integral of each spot, right? And I get c1, c2, minus 10 plus c3. To solve for c1, c2, and c3, I have to use my initial condition, right? That was given to me at the beginning, okay? So my initial velocity is 1, minus 1, and 3. So what I do is I say, this happens at time t equals 0, right? So we say v of 0 equals 1, minus 1, and 3. So it means everywhere I see a t, I plug in a 0, and that helps me solve for it. So let's do this. I'm going to go v of 0 equals 0 plus c1, 0 plus c2, minus 10 times 0 plus c3, and that was equal to 1, minus 1, and 3. So this one, I'm going to break out. I'm going to say 0 plus c1 is equal to here, is equal to 1, which means c1 is equal to 1. I'll take this piece here, 0 plus c2 equals this part, minus 1. That's c2 equals minus 1. I'll take this bit here and I'll set it equal to 3. minus 10 times 0 plus C3 equals 3. So this is 0 plus C3 equals 3, C3 equals 3. Okay, now I have my constants, which means I can use them to figure out my velocity at any time t. So I can plug that back in and I can say then v of t equals 1 minus 1. No, don't forget, this was equal to minus 10t plus c3. So this becomes minus 10t plus 3. This gives us our velocity. Okay, so that's our first part. They asked us to figure out, right, find its position as a function of time. I had to start with acceleration. Now I get to go with position, right? So position is antiderivative of velocity. Right, so I take the derivative of the position and the change in position over change in time, that gives me the velocity, right? So if I integrate my velocity, okay, then I'm going to get my position, right? You can think about, we usually write it like this, velocity is derivative of position, right? So x prime of t equals v of t. Okay, so if I integrate both sides, I'll get my position is the integral of velocity. Is what we're going to do. So we're going to use our acceleration to figure out our velocity to figure out our position. All right, so let's go ahead and do that. So I'm going to say x is equal to, x of t, sorry, is equal to the integral of velocity dt. So let's plug it all in. So my integral, I'm going to integrate this thing here. 1 minus 10t plus 3 dt. So this is equal to integral of 1 times dt, integral of minus 1 times dt, integral of minus 10t plus 3 dt. I'm going to integrate each individual piece. I'm going to get new constants I have to worry about, and I'm going to get a vector answer at the end. Okay, so when I integrate this, I'm going to get 1 times t dt. This becomes t plus c1. This is minus t plus c2. This is, remember our power rule, this is going to be minus 10 t squared all over 2 plus 3 times t plus c3. And this is x of t. Now again, I have to use my initial conditions to figure out what my C1, C2, and C3 are. Well, we were told a ball is thrown at 0, 0, 2. That's my initial condition of my position. So that's at t equals 0, right? So x of 0 equals this. So I can use that to help me. Guess I'm going to plug this in, and that's going to equal to 0 plus c1 minus 0 plus c2. This is going to become minus 5 times 0 squared plus 3 times 0 plus c3. Okay, c1 equals 0, c2 equals 0, and c3 equals 2, right? So I set each one equal to the other. Whew. All right, so I'm going to put it all back in order to get my final position, which I'll write down as x of t equals, this is going to become t plus 0 minus t plus 0 minus 5t squared plus 3t plus 2. I'm running out of space here, I'm sorry. Okay, so we had to take the antiderivative. We had to integrate, right, in order to get all the different pieces. Okay. I think my next example might be complex and I might want to spend a lot of time. Yeah. So my next example for here is actually quite complex, and I want to spend a nice amount of time actually thinking about it and setting it up. And so so what I'd like to do is I'll stop here so that we can pick up this on Monday of next week. I know this seems kind of short, but I want to actually have plenty of time because this problem it's going to take, you know, quite a while to explain and to draw out and to do stuff, okay? Because there's a lot of stuff that's happening here and I want to do it justice, okay? So I'm going to stop here so that you guys can take your quiz this morning if you want, or you can wait. It's a 24-hour window. It opens up at 11, okay? And it'll be open until 11 tomorrow morning, okay? So keep that in mind. And then don't forget that your homework is due tonight and your classworks are due. Okay, remember for the classworks for this stuff, I couldn't load the classwork, the PDFs into the assignment, but they're there on our modules page. You just have to do a handful of problems on each. Please don't do the whole thing. It's a lot of different problems, but there are solutions in there so you can check your answers. Anyway, I think that's about it. Okay, you guys, I hope you have a wonderful break and stay safe and stay healthy. And I will see you in a week. Okay. Have a great week, you guys, and good luck on the quiz today. Don't forget to take that.
All right, thank you.
Take it easy. Have a good break, guys.
You too.